Hello everyone, welcome to the Exam Ignite YouTube channel. Today I am continuing the next series of Electromagnetic Theory subject BEC401 subject derivation, important derivations and concept explanation series. Today we will start with the electric field and intensity. This is the part 2. For the part 1, check the description for the link and do watch the part 1 and continue with the part 2. Electric field and intensity. It is at any point in an electric field is force experienced by a unit positive charge placed at that point is called as an electric field intensity. Consider charge Q. It is located at a position A and at B in the electric field setup by Q. It is required to find the electric field intensity. According to the Coulomb's force law, we know that between the Q and the delta Q charge, differential Q charge, what is the force? Force is 1 by 4 pi epsilon naught Q into delta Q divided by R square. This will be the first equation. Now delta Q, it is a unit charge and let's consider the value to be 1. Then the force given by the electric field intensity will be what? E is equal to F. So what will be my F will become E and Q divided by 4 pi epsilon naught R square. This will be my second equation. Next is vector representation, where we will represent this equation in the vector form, that is E vector is equal to Q divided by 4 pi epsilon naught R square. This gives the electric field intensity at a point due to the point charge. There are two types of derivation here. First comes the point charge and then for the many charges. So point charge, you have to do this. For the many charges, if they ask, so it is based on the principle of superposition that states that force between any two charges is independent of the presence of the charge, due to which the effect of the individual charges would be superposed. So here consider a point P with there are many charges on which it is affected. So the field at a point to two or more charges in the vector sum is a vector sum of the fields that various charges could set up individually at the same point. Consider Q1, Q2 till Qn are the charges that are placed at what distance of R1, R2 till Rn from the point P. So let what the unit vectors be AR1 cap, AR2 cap till the ARN cap correspondingly. So electric field intensity at a point P due to the charges and will be what? E1 vector. For the one charge it will be E1 vector, that is Q1 divided by 4 pi epsilon naught R1 square AR1 cap. Similarly for the E2, E2 is equal to Q2 divided by 4 pi epsilon naught R2 square AR2. It goes upon the En vector, that is Qn divided by 4 pi epsilon naught Rn square. The total electric field at a point P due to all these charges can be written by using the principle of superposition, that is E vector is equal to E1 vector plus E2 vector till the En vector. So what it is summing up? So we use a summation symbol, we remove the constant outside, that is E vector is equal to 1 by 4 pi epsilon naught. Summation of I is from 1 to n numbers. Qi divided by Ri square into unit vector, that is Ari cap. So this gives the electric field intensity due to many charges. Next comes electric field intensity at a point due to number of point charges. So here we are having number of point charges and you have to find at a point. So consider there is an infinite charges over the elementary space M. Consider a small amount of charge, that is delta Q, in that place at a point P where we have to determine the electric field intensity. So R be the distance between that P point and the delta Q. So AR vector will be my AR cap will be my unit vector. Electric field at that point will be what? Delta Q divided by 4 pi epsilon naught R square into AR cap. Take it as equation 1. So let delta E vector is equal to dE vector, differential, small one, and delta Q is equal to dQ. So on replacing those two, we get an equation 2. Now electric field intensity at a P due to the entire charge distribution will be what? Integration of all those small differential electric fields, that is integration of dE vector, that is integration of dQ divided by 4 pi epsilon naught R square into AR cap. This is my third equation, final equation. Next comes electric field intensity at a point due to line charge distribution. This is generalized derivation. You have to know just to know about the formula. If the charge distribution is such that the charges are aligned continuously through a line, this is a line having a point charges, then it is called a line charge. So we are having a rho L, it be the line charge density of that, and that is defined as what? charge per unit length. So rho L is given as dq by dl, that is coulomb by meter. So what will be my rho L in terms of, this is for the small. For the regular one, we write it as delta q divided by dl of till from where delta L to 0 tends to 0. So finally, on rearranging this, we get dq is equal to rho L into dl. So we know that electric field intensity at a point, as we studied earlier, that is electric field is equal to integration of dq divided by 4 pi epsilon naught r square into ar cap. Substitute dq in this equation. Remove the constant outside the integral part, and substitute the dq as rho L into dl. You will get the equation, which is E vector is equal to rho L divided by 4 pi epsilon naught integration of dl divided by r square into air cap. This is an electric field intensity due to an infinite line charge. Next, similarly, you have to do it for the sheet of charge. That is, if there is a charge distribution is such that the charges are continuously distributed in a 2D surface, then it is called surface charge, or you can say sheet of charge. So consider a surface S where we have infinite charge distributed. So let rho S be what? Surface charge density. That is what? Charge by surface area. Rho S is equal to what? dq divided by ds. So rho S is small dq divided by ds, that is coulomb per meter square is a unit. Consider it as equation 1. We know from the electric field intensity, we know the general formula that E vector is equal to dq divided by 4 pi epsilon naught r square into AR vector. Since the charge distribution is continuous at the point P, due to that infinite charged sheet, we have to integrate all those small differential electric fields. So electric field is differential integration of that small differential electric field, which is equal to integration of that, remove the constants outside, you have to substitute the dq, that is what we have found here, rho s into ds. You will get the equation as electric field is equal to rho s divided by 4 pi epsilon naught integration of ds divided by r square into ar cap. This is an electric field intensity due to the infinite sheet charge. Electric field intensity at a point due to the continuous volume charge distribution. Here, if a charge distributed is such that the electric fields are continuously in a volume, consider now in a 3D place. So this is a volume charge distribution. Rho V be the volume density, where it is equal to charge by unit volume. Rho V is what? dq divided by dV. That is rho V is equal to dq by small dq by dV. That is coulomb per meter cube unit. We know from the generalized equation, same way as we done for the last two things, we have to integrate all those small differential electric fields. So on integrating and then replacing the dq as rho v into dv, we get the final equation as electric field intensity due to volume charge distribution is equal to rho v divided by 4 pi epsilon naught integration of dv by r square into ar cap. Now comes the major derivation, that is electric field intensity due to a line charge distribution. So consider a line AB, which is having an infinite line charge, straight line. It is a charge carrying along the z-axis. So rho L will be what? Will be our linear charge density. This is a very important derivation. Listen properly. So dq is a charge over a length, that is dz. Let me consider a charge here. Rho L will be what then? We know it is charged by length. So dq divided by dz. On rearranging, we can write dq is equal to rho L into dz. This will be my first equation. Next is we have one more point here, point P, which is at a coordinate of 0, y, 0. It is on the y-axis. Okay, it is a point at an electric field due to the line charge. We are comparing with the line charge. So R is equal to what? This is the distance between this O and P, that is R, which is perpendicular line that is joining the line charge. Next comes dz. Dz is what? Differential element that is at the position M. Now AR vector, it is a unit vector along the MP. We know electric field formula, that is dE vector is equal to dq divided by 4 pi epsilon naught r square into AR cap. This consider this as equation 2. Now you have to find the r vector to substitute here, right? So r vector is equal to what? For these two coordinates, you have to find the r vector. That is x2 minus x1, that is 0 minus 0, ax cap, and y2 minus y1, that is y minus 0, y cap, and then 0 minus z, az cap. So on simplifying it, what do we get? Y A y cap minus Z A y cap. So you know AR vector, that is a unit vector finding formula, is R vector divided by magnitude of R vector, as we learnt in the previous video, which is equal to what? Y, substitute this form, divided by R, that is our radius. Next comes the distance between them. That is, next comes, substitute this equation 3 and this equation 1 we had, that is for the dq, in this main equation. What do we get? Dq, we did it as rho L divided by dz divided by 4 pi epsilon naught r square into y into ay cap minus z into az cap divided by r. So we are having a triangle forming, that is what MOP. Let's see here, M, O and P. This is a right angle triangle. From this we can write z is equal to r cot theta. Consider this has theta here and write what is that? Cot theta is equal to z by r we get. So write in terms of z, that is r cot theta. Similarly, for write for cosecant theta, that is r is equal, small r is equal to capital R cosecant theta. So on differentiating this z, we get dz is equal to minus r. Cot theta differentiation is cosecant square d theta, and we can write y is equal to r. Is that clear? Next, we'll go to the main part. That is what we have to substitute all these things in this above equation, where rho L is same. What is dz here? Minus r cosecant square d theta divided by denominator. What do we have? R here, r cosecant theta, that becomes r square cosecant square theta. Now, y ay cap, what is y is replaced as r and ay cap minus, what is z? Z is what? R cot theta. Write that. R cot theta is az cap divided by small r is r cosecant theta. Here what happens? This get cancelled, r and r square get cancelled, cosecant square theta and cosecant square theta will get cancelled, d theta will actually remain here, and here r take common from the numerator and from the denominator, cancel it out. Remaining is minus, don't leave this, rho L d theta divided by 4 pi epsilon naught. This r is remaining and cosecant theta. Here ay cap minus cot theta can be written as what? Cos theta divided by sin theta. This cosecant theta gets cancelled with this cosecant theta. Clear? Here cosecant theta square theta and cosecant square theta will cancel, hence we take it outside here from the denominator. Next, right here minus rho L d theta, take it outside here. Cosecant theta can be written as sin theta, that is 1 by sin theta. So it goes to the numerator and rearranging just. Next is minus rho L divided by 4 pi epsilon naught r into multiply the sin theta to inside. So this becomes sin theta ay cap minus sin theta will get cancelled. So cos theta az cap into d theta. So as I said previously, we have to add all the small differential elements. So electric field is equal to what? Differential integration of dE vector, which is equal to minus rho L. Write all these things what you have obtained here, the equation right here. Now apply the limit. From where to where it has to go? From pi minus theta 2, which is the lower limit, to the upper limit theta 1. Clear? Now on integrating, sin theta will become minus cos theta, minus cos theta will become minus sin theta. Apply the limits for the both the ends, that is cos pi minus theta 2 plus of cos theta 2 into ay cap minus sin theta 1 minus sin theta 2, that is az cap. We'll get this on simplifying that. So finally, what do we get? Minus, take it common, it becomes plus rho L of cos theta 1 plus cos theta 2 into ay cap plus sin theta 1 minus sin theta 2 into az cap. So for the infinite length, what happens? We don't have this theta 1 and theta 2. So that gets removed. So final equation, what do we get? We have to cos theta 1 and cos theta 2, on putting this cos 0, we get 1. So 1 plus 1 is 2. 2 ay cap. Sin theta, it becomes 0, 0. So this whole component becomes 0. 2 ones are 2 2s are we can cancel here. So electric field is equal to rho L divided by 2 pi epsilon naught r into ay cap. This is our final equation. Next concept is electric field due to the sheet of charge, that is surface charge. Consider a surface here with a, let us consider a small differential area as dx and a charge of q forming, consider a point P which is at a distance of r from that sheet. This is a theta, angle theta. and this is along the axis y-axis. So as usual, rho L is given by what? Rho S into dx. So d vector is equal to rho L divided by 2 pi epsilon naught into AR cap. Consider this is equation 1 and this is our equation 2. This is taken from the previous one. Now differential Ey is equal to what? D is sine theta. This one, right? D is sine theta. So we know D is given as rho L divided by 2 pi epsilon naught r into sine theta. Next is rho L is again simplified as rho S into dx divided by 2 pi epsilon naught r sine theta. What will be my total electric field? That is integration of d. That is two components. One is x component and the y component. It is a sheet. It is placed in a xy plane. But here the x component will be 0. We are doing for the y component. So what happens? E is equal to integration of dey. Dey, that is equal to limit from minus infinity to infinity. Substitute this equation 3 here. Now from again here find the cot theta for this theta. What do we get? X by r is equal to cot theta. X is equal to r cot theta. Differentiated dx is equal to minus r. What is cot theta? Is minus cosecant square theta differentiation. Now find out for cosecant theta. That is r by small r by capital R. So small r is equal to capital R cosecant theta. If x is equal to minus infinity, theta is equal to what? Cot inverse of x by r. So theta will be pi. If x is equal to infinity, then theta will be 0. Now for that condition, electric field from pi to 0, this rho s dx, replace it with this term d theta and sine theta divided by 2 pi epsilon naught. Again r is changed with the capital R cosec theta square. Next we will move square is not there. Next we'll move, that is rho s divided by 2 pi epsilon naught. 2 pi epsilon naught of r cosecant theta. Apply the limit pi to 0. So here this and this gets cancelled out. Final remaining thing will be a minus d theta. So might take the minus outside, or else we can interchange the limits. Lower limit will go to upper limit and upper limit will come to lower limit. 0 to pi d theta. That is equal to what? Rho s divided by 2 pi epsilon naught into differentiation of d theta is theta. That is from 0 to pi. So from small 0 to pi, so here we get pi and pi will get cancelled. So electric field is equal to rho s divided by 2 epsilon naught a s cap. Electric field density. Consider 2 point charges, the electric field originating from the positive charge and terminating at the negative charge. So consider unit surface area now. With a net flux of flux lines passing through that area, that is called as an electric field density. D is equal to xi divided by S. So xi is equal to total flux and S is the total surface area. What is the vector form? D vector is equal to d psi divided by ds into a n cap, that is coulombs per meter square, whereby d psi is total flux lines passing through the normal through the ds differential area. ds is my differential surface area and a n cap is my unit vector normal to the surface area. Electric flux density due to the point charge. For a point charge, consider a point charge plus q placed at a center imaginary sphere of radius r. So flux lines is originating from that point charge, right? Plus q are directed radially outwards. So the magnitude of that flux density at any point on that charge is d is equal to total flux psi divided by total surface area, which is my equation 1. Next, magnitude of that is q divided by 4 pi r square. Vector form, write it as d vector is equal to q divided by 4 pi r square ar vector coulomb per meter square. Relationship between this d vector and e vector. Here e vector is intensity due to point charge. We can write it as q divided by 4 pi epsilon naught r square into ar cap. Ratio of this capital D by E. Write down both the formulas. Here everything gets cancelled out, except the thing is for this we don't have epsilon naught in this finding out D. Final that gets remained, 1 by epsilon naught will get remained. So on reciprocating that we get epsilon naught. So D vector is equal to epsilon naught times the E vector. For the free space, if you put it as 1, then epsilon naught into E vector. For some medium, we can add it as permittivity, that is epsilon naught into epsilon naught. E vector and D vector acts in the same direction. D vector and E vector are related through the permittivity of the medium in which the charge is located. E vector due to any charge configuration is a function of the permittivity epsilon naught, which is D vector is not. Next concept, electric flux density of various charge distribution, that is line charge, surface charge and volume charge. Rho L we know dq by dl. Put it into this d, that is q divided by 4 pi r square into a r cap. Substitute in the q place, you get integration of rho L dl divided by 4 pi r square. D is equal to what? 1 by 4 pi r square, constants are removed. Integration of rho L into dl into a r cap. So that is what q substitution. So line charge is an infinite, for an infinite length is rho L divided by 2 pi epsilon naught r into a r cap. So d is equal to, we know, epsilon naught into e. So finally we get rho L divided by 2 pi r into a r cap. Substitute e here. So epsilon naught and epsilon naught will get cancelled. Surface area, consider a sheet of charge having uniform charge density rho s coulomb per meter square. Electric field intensity due to the infinite sheet charges electric field is equal to rho s divided by 2 epsilon naught a n gap volume per meter. D vector is equal to epsilon naught into E vector. D vector is equal to rho s divided by 2 into a n gap. Volume charge is considered a uniform volume charge density rho v, that is coulomb per meter square. Electric field intensity due to infinite volume charge will be 1 by 4 pi epsilon naught r square into integration of v rho v dv into e r cap. So d vector is equal to epsilon naught into e vector. Substitute e vector. You get d vector has 1 by 4 pi r square volume integral of rho v into dv into e r cap. This was all about the first module. Part 2, part 1. Go through the part 1 and part 2. This completes the first module, all the important derivations that you need to study for the exam. For the next module, do subscribe the channel. Thank you.